Greetings everyone, this is Mr. Mall, and in this video we're going to be doing a lesson on kinetic, potential, and thermal energy. At the end of this video you should be able to define kinetic energy and perform calculations involving it. You should be able to define potential energy and perform calculations involving both elastic and gravitational potential energies. Lastly, you should be able to perform calculations relating work and change in energy and understand what thermal energy is. Let's go ahead and get started. So the first thing we're going to do is define kinetic energy. If an object is moving, it has energy due to its motion, and this is what kinetic energy is. To calculate for what kinetic energy mathematically is going to be equal to 1/2 mv squared, where m is the mass of the object moving, and v is the speed, not velocity, because energy is a scalar, the speed that the object is moving squared. When I look at the unit, we have kilograms times meters per second squared times meters, which gives us that final unit there. And a little note that I want to put in here is that when I'm trying to relate work and kinetic energy, in other textbooks they have what's known as the work kinetic energy theorem. And what that says is that the work done on an object is equal to its change in kinetic energy. Now our textbook actually takes a broader look at it, and it says that the work done on an object is just the change in energy in general. However, if only the kinetic energy is changing, the gravitational is the same, elastic's the same, all other energies are staying the same, then the work done on an object would be equal to just its change in kinetic energy. And AP questions in the past have used this approach to problems, so I put that in there. So we're going to do an example problem, and so in this example problem from our kinetic energy and work, we're going to have a 6 kilogram block that's initially sliding at 5 meters per second and later is moving at 8 meters per second. Okay, so what I should be noticing that it has some kinetic energy initial, and then afterwards we're at some kinetic energy final that's actually greater than, because it's going faster, it's going to have more kinetic energy. This means that energy must have been added to the block to get it going faster. And because there's no other types of energy, it doesn't say anything about, well, we're going to talk about gravitational potential and elastic potential, but really the energy that it has is just due to the fact that it's moving. And so when I rearrange that, we get that nice work energy equation that the overall work done on the object is just going to be the change in its kinetic energy. So the first question says calculate the initial kinetic energy of the block. So to find the initial kinetic energy, I take my equation 1/2 mv squared, and I'm going to go ahead and look at my object. The mass was 6 kilograms. It was moving 5 meters per second. And we're going to get that that object had 75 joules of kinetic energy to start. The next question says, calculate the work done on the block to cause its increase in speed. So we saw just a moment ago that some work was done to give energy to the block to make it go faster. And because kinetic energy is the type of energy involved, then our net work is going to be equal to that, well, I may kind of go backwards and say, okay, well, I want to find the work, and I just remember that, oh, the work is equal to FD cosine theta. Okay, this is true, but probably not useful here, because they don't tell me anything about the force applied, and they don't tell me how far it was moving. So this is not going to be the appropriate way to find the work done. So I know that the work done is the change in energy. Oops. And the change in energy in this case is all kinetic energy. So the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. So we already calculated the initial kinetic energy. Why don't we go back and calculate the final kinetic energy? So 1/2 mvf squared. And we're going to get that our final kinetic energy, we're going 8 meters per second, is going to be equal to 192 joules. So when I go back now, I can figure out what that change in that change in energy, or the work done to get that object up to speed, and that difference in energy is going to be the 192 joules minus 75, and we're going to get that our change in kinetic energy is 117 joules, which is going to be the work done on that object. All right, let's do another example. In this example, it says a 1,200 kilogram car is traveling at 18 meters per second when it applies its brakes. If the brakes allow friction to exert 2,000 newtons of force on the car, and the brakes are applied for 50 meters, how fast is the car moving when the brakes are released? Okay, so I'm immediately noticing some things here. They give me a force, they give me a distance, they give me a final velocity, they give me an initial velocity, and they give me a mass. And so I'm thinking velocity, I'm thinking kinematics, but they also give me the force applied and the distance through which that force was acting. So if a force is applied over some distance, I'm thinking that work is being done in order to change that object's energy situation. So because it's moving horizontally and the only change before and after is going to be in its speed, it's not going up a hill, it's not going into a spring, is going to be that the changes in its kinetic energy. It changes speed. So I know that in this case, that net work done is going to be equal to the change in energy, which is all kinetic. And so I know that the net work done on the object is equal to F d cosine theta. Okay, this is going to be a useful equation in this problem. And then the change in kinetic energy was the final kinetic energy minus the initial kinetic energy. So I'm going to go ahead and I'm actually going to be able to solve for VF here because I actually have all this information. I have the force that was applied. I have the distance through which it was applied, 50 meters. And as I'm looking at my car buzzing along, when it's braking, the force is going to be frictional force. So if I'm going in that direction and the force of friction is in that direction, when I get with that cosine theta, make sure that I include that that is acting 180 degrees, because that angle is the angle between the force of friction and the displacement, which was to the right. So I'm going to have to plug in cosine 180 degrees there. And then I can plug in the rest of this here. 1/2 the mass was 1,200 kilograms times VF squared, I'm trying to find that, minus 1/2 times 1,200 times, we started moving at 18 meters per second. Got to square it, don't forget to square it. When I rewrite this and get some values in here, we're going to have negative 100,000 is equal to 600 VF squared minus 194,400. And when I get VF by itself, we're going to get the final velocity would be 12.5 meters per second if that much force was applied over that distance. It's going to change the energy, it's going to slow it down. And there's our final velocity. All right, let's do another example now, or let's talk about potential energy. So we're going to talk a little bit about potential energy. Feel free to pause this video. Potential energy is the energy of a system due to its condition. So when I'm thinking potential energy, I'm thinking that there's energy stored somewhere. It could be in a spring, it could be stored in a gravitational field. And so one type of energy, potential energy, would be the gravitational potential energy. And this is energy stored in a gravitational field. If I think of an object with a gravitational field, remember we looked at those gravitational field lines. So where's the energy stored? The current theory says that if I put an object with mass in a gravitational field, what it will do is it will distort the gravitational field. And by distorting the gravitational field, it stores energy in the field. depending on where that object is in relation to the object's center or its distance away, look at that little y there, depending on how big the mass is, the gravitational field strength, and how far it is from the center of the other object, it's going to distort the field more or less, and there's going to be more energy stored in the field. And as that object is released, it will go to the place of lowest energy, which is closer to the planet, and we'll see that stored energy turn into other forms. So this is the equation. The gravitational potential energy of an object, U sub g. U is a standard way to denote energy that's stored. M is the mass, g is the gravitational field strength or acceleration, and then y is the vertical height above some arbitrary zero level. So that arbitrary zero level could be the surface of the planet, it could be the top of a table. It all depends on the problem that we're setting up. We decide where zero is, and then we measure the height above that position. Just a little note here, AP will sometimes and often use an H instead of Y in problems, and so will some of the homework questions. So H and Y can be used interchangeably. They switched to Y. It used to be H. Okay, so other forms of this equation, on your equation sheet you'll see delta UG is equal to mg delta Y. And this is just if our gravitational potential energy is changing due to some change in height. We can just look at the change in gravitational potential energy and the change in height. Our units are going to be what you would expect by taking mass and then meters per second squared times a unit of meter, or height. And that's also a joule. We're talking about the same thing here. Another type of potential energy is elastic potential energy, and elastic potential energy is spring or elastic potential energy, and it's denoted with a U sub s, and the equation is 1/2 kx squared. Now, if I have energy stored in a spring, K is going to be the stiffness or springiness of that spring, and K stands for the spring constant in units of newtons per meter. So if I have like let's say I had a 5 Newton per meter spring constant, that would mean that for every 1 meter that I stretch that spring, it would take an additional 5 newtons of force to stretch it. Okay, 5 Newton per meter. So the bigger that number, the stronger or stiffer the spring. And then I also have to multiply that by x squared, where x is the distance that I stretch or compress that spring from its equilibrium or where it was originally before I started stretching or compressing it, that equilibrium length. Alright, so let's go ahead and use some of these equations in some simple problems so you can see how we can use these. So the first question is going to be involving, we have a mass hung from a spring, and I'm going to go ahead and draw a little picture over here. So I've got a mass hung from a spring, and it says that when I hang this mass from the spring, it's going to stretch down that spring a distance of 1.47 meters. Okay, so I'm going to call that x because that's the distance that it was stretched from where it was. Okay, it probably used to look like this. That's kind of the before picture. And then after, we've got this kind of going on. So there's my stretch distance. So what we can do is we can figure out what that increase in elastic potential energy of the spring is. So before I get too excited with knowing the before situation, I actually don't know how much the spring was stretched beforehand. I actually don't know if it was at its equilibrium length. So I could always find the change in elastic spring potential by taking the final elastic spring potential energy minus the initial. In case I didn't know if it was even at its equilibrium length, I could start from here. Now in this case, this is if it might already be stretched. I'm going to assume, and I'm going to call that it was at an initial of 0, so that it wasn't stretched before, to make this problem a little bit easier. And if it wasn't stretched before, then it's just going to be equal to that spring constant, which is given. and the spring constant is 200 newtons per meter. And once I hang that down, it's going to be stretched out. I'm going to say 1.47 meters. We're going to square that, and we're going to get, I'm going to subtract 0 because it was not, I'm going to assume that it wasn't stretched before. And when I do that, I'm going to get that there was 216.1 joules of elastic potential energy change. Okay, so we stretched out that spring. Now there's some energy stored in stretching it. Okay, the next question says calculate the decrease in gravitational potential energy, so U sub G, of the mass. Okay, so the mass was at some height above the ground, and so now its vertical position has changed. And so I'm going to use this lowest level here. I'm going to set this as my y is equal to 0, or h is equal to 0, the lowest position. And so my mass used to be up there. And so whenever there's a change in height, then there's going to be a change in gravitational potential energy. So to calculate that change in gravitational potential energy, mg delta y, I can look at how the mass's energy situation was changing. So I had a 30 kilogram mass. It was on the 9.8, and then we have some delta y. So my change in position, if I call my change in position is always going to be final minus initial. So my final height, I'm going to call that to be my final height is going to be, actually, you know what, I'm going to do, I get to choose where 0 is. So I'm going to actually make the initial position of the mass 0. And so that final position is going to be negative 1.47 minus 0. I'm going to call that negative, and it really doesn't matter which way we do it. But what I'm going to do here is I'm going to get a final value of negative 441 joules of energy change, the decrease in the gravitational potential energy of the mass. And so that's going to be the amount of energy that the gravitational field unloaded onto the spring to stretch it out that far. Now you may be asking why it's not 216 joules. If the spring now has 216 joules of energy, but the gravitational field lost 441 joules, where did that go? Maybe the spring is still moving. Maybe it was a rusty spring, so there's some thermal energy. A couple of different possibilities. Okay. All right, the next thing that we're going to do is I'm going to talk a little bit about thermal energy, and then we'll be done. So the book uses the words delta ETH to talk about the change in thermal energy. Okay, you rub your hands together, you're thinking thermal energy. So it turns out that the change in thermal energy is going to be the amount of energy that's done through work by non-conservative forces. And a non-conservative force is a force interaction that does not store useful energy. In other words, it's not stored in the gravitational field, it's not stored in the spring, it's not stored in the motion of an object that I can actually use. And so this type of energy is going to be thought of as the change in thermal energy. And this is going to occur when particles in the system and the surroundings are going to be having faster random motion. And that faster random motion, you can also think of this as dissipated energy. It's energy that we can't really get back. Once it's dissipated or it's turned into thermal energy, in most of our physics problems, when we get to chemistry, we can use it, but it's not going to be useful for physical changes in this class. And so that's going to be a little wrap up of thermal energy and potential and kinetic energy, and I hope that this was helpful.